7 or 8 years ago, our algorithms would look at an image and they'd be able to predict sort of one overall concept. Nowadays, fast forward just a few years, the computer vision algorithms are able to look at an image and explain in words what is the nature of the object that's shown in the image.
This is exactly what Meta has been working on in the last few months. They just released a model called SAM. Segment, anything model that can detect and segment almost anything in the image. In this video, we're going to dissect the SAM model, try to understand how it works, what was the data used, and so on. Let's deep dive. SAM is the first foundation model for segmentation. It has one-click segmentation system with zero-shot generalization to unfamiliar objects and images without the need for additional training. We tried it, and its accuracy is simply outstanding. But before we dive into the model, let's first try to understand what segmentation exactly means. I really like this video from Stanford professor Justin Johansson, where he explains segmentation concepts. You can find link in the description for now. Let's hear from him.
So the last task that I want to talk about is this idea of instance segmentation. So here, instance segmentation is in some ways like the full problem. We're given an input image, and we want to predict, the locations and identities of objects in that image, similar to object detection. But rather than just predicting a bounding box for each of those objects, instead we want to predict a whole segmentation mask for each of those objects and predict which pixels in the input image corresponds to each object instance. So this is kind of like a hybrid between semantic segmentation and object detection, because like object detection, we can handle multiple objects and we differentiate the identities of different instances. So in this example, since there are two dogs in the image, an instance segmentation method actually distinguishes between the two dog instances in the output. And kind of like semantic segmentation, we have this pixel-wise accuracy, where for each of these objects, we want to say which pixels belong to that object.
Let's first look at the data set they used. To generate the data, they used Data Engine, which has 3 stages: assisted manual, semi-automatic, and fully automatic. The final data set includes more than 1 billion masks from 11 million licensed and privacy-preserving images. Note there are no class labels for the images or mask annotations. They start by translating the idea of a prompt from NLP to segmentation. They choose this task because it leads to a natural pre-training algorithm and a general method for zero-shot transfer to downstream segmentation tasks via prompting. Segmentation is a broad field. There's interactive, foreground, semantic, instance and panoptic segmentation, edge detection, superpixelization, and object proposal generation. Meta used a composable design that can do many of these tasks together. Model has 3 components: an image encoder, a flexible prompt encoder, and a fast mask decoder. They are built on transformer vision models amortized for real-time performance. For a prompt encoder, they use 2 sets of prompts: sparse, points, boxes, text, and dense masks. They represented sparse prompts by positional encoding summed with learned embeddings for each prompt type and free-form text with an off-the-shelf text encoder from Clip. Dense prompts are embedded using convolutions and summed element-wise with the image embedding. The mask decoder efficiently maps the image embedding, prompt embeddings, and an output token to a mask. It augments transformer decoder block by a dynamic mask prediction head. Their modified decoder block uses prompt self-attention and cross-attention in 2 directions, prompt-to-image embedding and vice versa, to update all embeddings. After running 2 blocks, they upsample the image embedding, and an MLP maps the output token to a dynamic linear classifier, which then computes the mask foreground probability at each image location. To rank masks, the model predicts a confidence score with estimated IOU for each mask. The model generates masks within 50 milliseconds. They supervise mask prediction with the linear combination of focal loss and dice loss. They filtered the masks with IOU score of below 0.88. SAM is designed for generality and breadth of use rather than high IOU interactive segmentation. Model had following hyperparameters: Atom dodge optimizer with linear learning rate and a stepwise learning rate decay schedule. The batch size was 256 images. To regularize SAM, they set weight decay to 0.1 and apply drop path with a rate of 0.4. No data augmentation is applied. They initialize SAM from an MA pre-trained VTH. The training was distributed across 256 GPUs due to the large image encoder and high-quality input. To limit GPU memory usage, we train with up to 64 randomly sampled masks per GPU. Additionally, lightly filtering masks to discard any that cover more than 90% of the image qualitatively improves results. For ablations and others variations on training, they augment the input with large-scale jitter. For ethical consideration, they trained SAM on licensed images. Responsible AI analysis of the work by investigating potential fairness concerns and biases when using the datasets and model. They focus on the geographic and income distribution and fairness of SAM across protected attributes of people. They also provide dataset, data annotation, and model cards for transparency to investigate SAM's fairness at segmenting people. More inclusive annotations for people, MIAP dataset was used. SAM marks a new chapter in the story of computer vision, demonstrating the power of foundation models in transforming the way we perceive and understand the world around us. The model is a big step ahead in image segmentation, but there is still work to be done. That's all from our side. Please like and subscribe if you haven't already. Also, let us know what you think about the model and if you have tried it out.